right, today we're going to tune into a hidden world, a kind of symphony that's happening all around us. We're talking about waves. We're going to explore how they move, how they interact, and, how these interactions can create everything from your favorite song to, believe it or not, complete and total silence. So let's jump right in.
I know, it sounds like a trick question, right? But it's actually the real science behind noise-canceling headphones. You pop them on, and suddenly the roar of a jet engine or all the chatter in a busy coffee shop it just melts away. So how is that even possible? To figure that out, we first need to get to know the main players in this story. So before we can get to that grand finale of silence from sound, we have to start at the beginning. We need to meet our main character, the progressive wave. This is kind of your classic, everyday wave, the one that's all about carrying energy from one spot to another. Just picture tossing a pebble into a calm pond. You see those ripples moving outward, that disturbance moving across the water? That's a progressive wave. It's carrying energy for sure, but the actual water molecules, they're mostly just bobbing up and down in place. They aren't traveling with the ripple. And that idea, transferring energy without transferring matter, that is absolutely the key to everything else we're going to talk about.
Yeah, waves don't usually just travel on forever. Eventually, they're going to run into something, like our ripple hitting the edge of the pond or a sound wave hitting a wall. And when it does, it bounces back. We call this reflection. But, and this is a big but, how it reflects really depends on what it hits.
Okay, so check this out. We've got two totally different results here. On the left, when a wave hits something fixed and solid, a denser medium, it actually flips upside down. A crest comes in, a trough bounces back. But look at the right. If the end is free to move, a rarer medium, the crest just reflects back as a crest. So the takeaway here is huge. The boundary type completely changes the game.
Okay, so now we know what waves are and what happens when they hit a wall. But what about when they hit each other? What happens when two waves try to occupy the same space at the same time? Well, this is where the real magic happens, and it's all governed by one simple, elegant rule, the principle of superposition.
So let's imagine two waves, perfectly identical, heading right for each other. We say they're in phase, which is just a way of saying their peaks and valleys, their crests and troughs, line up perfectly. So what do you think happens when a crest from one wave meets a crest from the other?
They literally build on each other. The two crests add up, and for just a moment, you get one big super wave with double the height. This is called constructive interference, because they're literally constructing something bigger. It's an amplification.
All right, now for the flip side. What if the waves are perfectly out of phase? This time, a crest from one wave lines up exactly with a trough from the other. This right here is the key to our headphone mystery.
And just like that, they're gone. The upward pole of the crest is perfectly canceled out by the downward pole of the trough, and in that instant where they overlap, the result is nothing. A flat line. Silence. That is destructive interference. And that's exactly what your noise-canceling headphones are doing. They're creating a sound wave that's a perfect mirror image of the outside noise, and the two just cancel each other right out.
And here's the official rule for all that cool stuff we just saw. The principle of superposition. It sounds kind of technical, but all it's really saying is that when waves cross paths, you just add them up at every single point. It's a surprisingly simple rule that leads to some really incredible outcomes. Now, what if you get this constant interference happening? Like, imagine a wave on a guitar string that travels to the end, reflects back, and starts interfering with itself over and over. You get something pretty wild, a wave that doesn't even look like it's traveling anymore. It looks like it's standing still. So let's put these two side by side. Our progressive wave, on the left, is all about traveling and transferring energy. But a stationary wave, or a standing wave, is stuck in one place. It just vibrates. You'll notice some points are moving like crazy, and some aren't moving at all. And what's really important is that no energy is actually being sent down the line. It's all contained.
So let's take a closer look at this thing. It has a really clear anatomy. The points that are totally motionless, we call those nodes. And the points that are vibrating with the biggest amplitude, those are the antinodes. They always show up in this alternating pattern, creating these beautiful, shimmering loops you see when you pluck a guitar string. Okay, so superposition has another cool trick up its sleeve. What happens if the two waves that meet aren't exactly the same frequency, but are just really, really close? Well, you get this weird auditory effect that musicians actually rely on all the time for tuning their instruments. The result is what we call beats.
You hear the sound get louder and softer over and over in this wah-wah-wah pattern. What's happening is the waves are slowly drifting in and out of phase with each other. So you get these moments of constructive interference where it's loud, followed by destructive interference where it gets quiet. And the closer the frequencies are, the slower that wah-wah beat becomes.
Okay, so let's bring this all home. We've seen how waves can interfere to get bigger, to disappear entirely, and even to form these cool standing waves. Well, it turns out this is the very physics that makes music possible.
So when you pluck a guitar string, it's not just vibrating in one big, simple loop. It's actually vibrating in a whole combination of these stationary wave patterns all at the same time. The simplest one, that single loop, gives you the fundamental frequency. That's the main note you hear. But it's also vibrating in 2 loops and 3 loops and so on, creating all these higher-pitched sounds.
Now, these higher frequencies are called overtones. And this quote really gets to the core of it all. The specific mix of overtones that are present is what gives any sound its unique character.
And this is what we call timbre, or sound quality. Think about it. A piano and a violin can play the exact same note, the same fundamental frequency. But the reason we can tell them apart instantly is because their recipe of overtones, the unique blend and volume of all those other higher frequencies, is totally different. Each instrument has its own unique wave symphony.
So there you have it. We started with a riddle about making silence from sound, and we ended up at the heart of what makes music, well, music. Superposition is happening all around us. So the next time you put on your headphones or listen to a song or hear an instrument being tuned, you'll know you're hearing this incredible, invisible dance of waves. Now that you know the rules, what else will you notice? Thanks for joining me.